Hello everyone, welcome to my channel Chemistry is Fun. Now see, in my previous videos I have already started discussing the topic states of matter. In that we are doing gaseous state. In the gaseous state we are studying about the gas laws. We have discussed about Boyle's law, Charles' law. Today I will be teaching and discussing Graham's law of diffusion and Avogadro's law. These two laws I will be dealing with today. Now see, if we have two gases and they should be non-reacting gases, and if we keep the gases side by side, then there is a tendency of the movement of molecules of one gas into the other, and this movement takes place from an area of high concentration to an area of low concentration. That is, the particles will spread through the medium from higher concentration to lower concentration area. This is a very common phenomena which we find if we have an incense stick which is lit up in one corner of the room. That fragrance spreads to the other corner of the room as well. Same phenomena if we spray some perfume at one end and we get the smell at the other end. Now all these are because of diffusion phenomena. Now regarding this, one law has been given, that is Graham's law of diffusion. This Graham's law states that if there are two or more non-reacting gases, so the gases should not react. If they react, they will produce a new product. So there we cannot define the process of diffusion. So it is stated that the gases are non-reacting. And such gases are kept near each other, then they have the tendency to mix spontaneously. They will mix with each other spontaneously, and they will form a homogeneous mixture slowly. So this ability that the gases mix spontaneously and they form a homogeneous mixture, this is diffusion. So this process is known as diffusion. Graham's law of diffusion is also applicable to another phenomena, effusion. So it is necessary to state that also. What is effusion? It is a process in which the gas is allowed to escape under pressure. Now, when a gas is in a closed container and pressure is applied on it, then there is a chance that the gas will be escaping out. If there is a fine aperture, also called orifice, in the wall of the closed container, then the gas can escape. This method is called as effusion. That is, if there is a gas in a container and the container has a small aperture, through the aperture the gas will be escaping out. This method is, or this phenomena or process is effusion. So this new term also should be known. Now Graham's law of diffusion states that if there is constant temperature and pressure, if these two physical parameters are constant, then the rate of diffusion, I already stated what is diffusion. The rate of diffusion of a gas will be inversely proportional to the square root of its density. Okay, we can mathematically state it like this: rate of diffusion is inversely proportional to density. So if rate of diffusion of the two gases, gas number 1 and 2, is given by R1 and R2 respectively, then R1 by R2 will be equal to square root of D2 by D1, because there is an inverse relationship to the square root of the density. So R1 by R2 is equal to square root of D2 by D1. Also see, this is D2 is the density of second gas, D1 is the density of gas number 2. If I divide this density by the density of hydrogen, we can get the vapor density. So we can also relate it to the molecular mass. So the rate ratio R1 by R2 will also be equal to square root of M2 by M1. Square root of M2 by M1. So it depends upon density but inversely proportional. There is no direct proportionality. Now, rate of diffusion can also be found out if we know how much volume of gas has diffused and the time taken. To find out rate of any phenomena, time taken is the criteria. So, rate of diffusion is given by volume of gas diffused by the time taken for the diffusion. Now, let's say there are two gases which are having the same volume, but they have taken different times for diffusion. Okay, there are two gases. For the first gas, time taken for diffusion is T1. For the second gas, the time taken for diffusion is T2. Then R1 by R2 is given by V by T1 divided by V by T2. R1 is V by T1. V is the total volume which has diffused, and this V is common for both because it is same volume. We have stated the volume is same. So it is V by T1 divided by V by T2. And we know that R1 by R2 is inversely proportional to D2 by D1. So V by T1 divided by V by T2 will also be equal to square root of D2 by D1. That can also be related to the molar mass as equal to square root of M2 by M1. V is common, so V gets cancelled. So finally we get the ratio of the time taken as T2 by T1 equal to, from this previous equation only we get, because here V gets cancelled. So we get T2 by T1 equal to square root of D2 by D1, that is also equal to square root of M2 by M1, where M is the molar mass. So if the density on molar mass is more, either time taken will be more. T2, D2, M2, C all are equally related, but the rate will be reversed. If density is more, rate will be less, because there is inverse relation between rate of diffusion and density of the gas. Next we can have a look at the comparison of volumes of gases that diffuse in same time. Here we keep the time constant. Okay, time is constant. The volumes of the two gases are denoted by V1 and V2. Again same formula, R1 by R2 equal to, R1 is V1 by T because T is constant. Same for both. R2 is V2 by T, so in place of R2 we write V2 by T. Here T is same, so TT gets cancelled. So we get R1 by R2 equal to V1 by V2. More the volume diffused, more is the rate naturally. And that will be equal to, as usual, square root of D2 by D1 equal to square root of M2 by M1. Now if the diffusion is going on and there is pressure applied to it, then naturally the rate of diffusion will be directly proportional to pressure, and we know R is inversely proportional to square root of M. So we can say that R is proportional to P by square root of M. And if we are comparing rates of two gases R1 and R2, then R1 by R2 will be equal to P1 by P2 square root of M2 by M1. Higher the pressure, more will be the rate. That is rate of diffusion. Now, based on these concepts we have just discussed, we can go through some numericals which will help you to have a better grasp on these concepts. Now see, the first numerical states that 50 volumes of hydrogen takes 20 minutes to diffuse out of a vessel. Okay, total means volumes can be any unit, so it's just stated volumes. How long will 40 volumes of oxygen take to diffuse out of the same vessel under the same conditions. Now see, volume, we are writing here 40 volumes and here we have written 50 volumes, means both the volumes units will be same, whatever we are taking, same for both. So let us approach how to do. Now for H2, hydrogen. For hydrogen, rate of diffusion can be stated as R1. I am stating it as R1. That is equal to total volume. How many volumes we have taken? 50. For you see 50 volumes. So it will be 50 by 20 because 20 minutes taken. So R1 is equal to 50 by 20. Now for oxygen, this is for hydrogen. Next, rate of diffusion of oxygen. This will be again, I am denoting it by R2. So this will be 40 by T because time only we don't know. 40 by T. Now there is a relation between the rate and the mass of the molecule. So we know that for hydrogen, the mass is 2, we know it. The same thing for oxygen is 32. So now let us, using the formula, what we get, the rate R1 for hydrogen was 50 by 20 divided by 40 by T for oxygen. That will be equal to square root of 32 by 2 because M2 will go up now. It was square root of M2 by M1. So 30, this will be square root of 16, that is equal to 4. So this becomes 50 by 20, we calculate it, 50 by 20 into T by 40 equal to 4. We have to find out the value for T. It will be 4 into 40 into 20 by 50. 0, 0 gets cancelled. Then here 5 8s are 40. 4 into 8 into 2, that is 64. The unit will be minutes. Because you see in the question, it was given minutes for hydrogen also, the unit will be same. So it is 64 minutes. So this should be the approach. Next is, we know that for uranium we have isotopes. One is uranium-235, another is uranium-238. Now we have uranium hexafluoride with the two isotopes. And we have to calculate the relative rates of diffusion of uranium-235, means isotope uranium-235 with that uranium hexafluoride. Another uranium hexafluoride in which uranium isotope present is U-238. Now in the gaseous state, what will be the relative rates of diffusion? For that, first we need to find out the molecular mass. So let us do it one by one. First we calculate for uranium 235 UF6. That will be equal to 235 plus, there are 6 atoms of fluorine, so 6 into 19, That comes out to be 349. Next we calculate the mass for 238. Uranium hexafluoride. That will be 238 plus 6 into 19. That comes out to be 352. Multiplication and addition can be done easily. Now we get the ratio of R1 by R2. That will be equal to square root of M2 by M1. Inversely proportional. That is equal to square root of 352 by 349. On calculating, we get it as 1.0043. So this calculation part is simple. We have to just take the find out the fraction value and then square root. So what we get ultimately, R1 by R2 equal to 1.0043 by 1. That is R1 is to R2 equal to 1.0043 is to 1. Okay. So first one was uranium 235. Its molecular mass is less, so its rate will be more. You see the ratio 1.0043 is to 1. Next, as I stated, we will go through another law also, Avogadro's law. Avogadro's law states that if we take equal volumes for any two gases and we maintain the same temperature and pressure, then they both will contain same number of molecules. And for this we also need to know what is molar volume. The volume which is occupied by 1 mole of a gas is called as the molar volume. And if we are taking equal volumes for any two gases, temperature, pressure is same. Number of molecules will be same for both. Now, molar gas volume for a given temperature and pressure, it is a constant. It does not depend on nature of the gas. At STP, the molar volume is 22.4 liters. That is VA. Molar volume is 22.4 liters per mole for 1 mole. So we can mathematically state Avogadro's law as V is directly proportional to N, or V1 by N1 equal to V2 by N2. So there is a direct relationship between the volume and number of volume of 1 mole of a gas. So number of molecules, which indirectly constitute number of moles, that is related to volume. Now based on this also we can do some numericals to just have a better understanding of the law. The first question states that 1 mole of a gas under given condition of temperature and pressure has volume 22.4 liters, and we know V equal to Kn. What is the value of K? See, it is 1 mole, so N equal to 1. And V given as 22.4 liters. So K equal to V by N from the formula is also given only. K equal to V by N, that is 22.4 divided by 1. So it comes out to be 22.4 liters per mole. Next question. 2 moles of helium gas fill up an empty balloon to a volume of 2.5 liters. What would be the volume of the balloon if an additional 1.5 moles of helium gas is added at constant temperature and pressure? So initially how many moles? That is initially N1. So what is N1? N1 equal to 2 moles. And V1 equal to 2.5 liters. It's given. Now N2, additional 1.5 moles added. So N2 will be 2 mole plus 1.5 moles. It is 3.5. Now as per the law, Avogadro's law, we know that V1 by N1 will be equal to V2 by N2. So from here we can state that V2 equal to V1 by N1 into N2. V1 by N1 into N2 in the numerator. Putting the values, just put the values. What was V1? V1 2.5 by N1 is 2 into 3.5 because N2 is 3.5. On calculating we get this as 4.375 liters. So this is V2. Next, let us have a look at one more question. 40 grams of nitrogen gas is kept in a 2.5 liter container. The gas exerts a pressure of 2 atmosphere on the container. If the pressure is kept constant, what is the final amount of gas in grams present in the container if gas is added until the volume has increased to 4 liters? So we have to, the volume should be increased to 4 liters. Okay. Now let us first write down all the data given. Mass of nitrogen given 40 gram. So mass nitrogen is equal to 40. Now N1, mass by molar mass. N1, mass given is 40. For nitrogen, molar mass 28. If we divide, we get 1.43 m, 1.43 moles. That is N1. And V1 given is 2.5 liters. We have to expand it to V2 equal to 4 liters. Now we know V1 by N1 equal to V2 by N2. So from here we get N2 equal to V2 by V1 into N1, putting the values. V2 is 4, V1 is 2.5 into N1 is 1.43. After calculating all these, we get 2.29 moles. 2.29 moles. Now we know the number of moles. We have to calculate grams of nitrogen. So you multiply it by molar mass. So amount of nitrogen will be equal to 2.29 we just got into 28. That gives, if we just multiply, we get 64 grams. So this is the final answer. So students, I hope you could understand the concepts which I discussed today. I also hope you have understood the numericals. If you have any doubt or you want me to explain some other topics, you can just put it in the comment section. Thank you for watching my video. Please subscribe to my channel. Thanks for watching. Please subscribe to the channel. Thank you all.